This video is going to give my solution to the capacitor example. I forgot to mention this earlier, but you can go out to Canvas and download some R scripts. So this R script gives my code for all three of these examples. It also has my R code with the solutions to the your turns that follow in the course packet. All right, so here's the situation. We're soldering capacitors to some motherboard, and the motherboard is made out of, it's called a substrate here, made out of one of three materials. We have four different bonding materials that we're testing. Okay, so bonding materials A, B, C, and D. And so I'm going to go over to R and run all this stuff live. So let's go read the data set in. And the first thing we might want to do is just look at how the substrate, so the material that the motherboard was made out of and the bonding material, you're going to see we have four replicates of each combination of substrate and bonding material. Now, I can go off and compute some means if I want. And so these would be the mean strength of these bonds. So which of these solder bonds is strongest is really what we want. Or we could do that with dplyr and you'll get the same numbers that I got earlier. All right, well, let's go make ourselves an interaction plot. So another command that is really useful is with. If you get sick of typing capacitor $, you can just say with this data frame, then when I specify the variables in interaction plots, I don't have to say capacitor $. So let's just go look at this. So in this particular interaction plot, I put the substrate on the horizontal axis, and I have different lines for the bonding materials, and I've used different colors. So then the question is there an interaction? And if we have non-parallel lines, which these lines are clearly non-parallel, that indicates there's an interaction. Now, it helps to interpret the interaction. So what I see here is bonding material 4 wins. It doesn't matter what the substrate is, whether it's A, B, or C, bonding material 4 gives us by far the strongest bonds. Now, there's a problem with bonding material 4. It turns out that that's the most expensive one. So I'd rather not use bonding material 4 if I could avoid it. So then the question is, can I get strong bonds using a different, cheaper bonding material? The answer is yes, but it depends on the substrate. So it looks like bonding material 1 works really well with substrate C, but bonding material 1 with A or B would be an absolute disaster. It looks like bonding material 2 works pretty well with B, but it doesn't get along with C at all. So 3 with C is a bad idea. Sorry, 2 with C would be a bad idea. Looks like bonding material 3 works pretty well across the board, but maybe not as well as material 1 with substrate C, maybe not as well as bonding material B with substrate B with bonding material 2. All right, sometimes it helps to look at it the other way. So what do I mean by the other way? Let's put bonding material on the x-axis, use different lines for substrate. And so what you'll see is bonding material 4 is by far the best. Doesn't matter what substrate you're using, it wins. Same conclusions across the board. So C works well with 1, and you're going to see that bonding material 3 works almost as well as bonding material 4 across the board. All right, well, we have the same question we had before, which is this significant? Are we just reading noise? So I'm going to go fit a linear model. Here's my linear model. And again, we shouldn't look at the parameter estimates just yet, but I'm going to look at them just to figure out what they are. All right. So what you'll see is that we have 3 dummies for the bonding material. Bonding material 1 is your base. Got 2 dummies for the substrate. Substrate A is your base. And then we have all combinations of those, so it's going to be 3 times 2, or 6 parameters to represent the interaction. Well, let's go do a drop 1. And notice the interaction term has 6 degrees of freedom. So what are those degrees of freedom? We're going to constrain all 6 of these product terms to be 0. So in other words, there is no interaction. In this case, the interaction is very highly significant. We're going to reject the null hypothesis and conclude that at least one of these products is non-zero, and in fact, quite a few of them are. All right, and so that's about all we need right now there are ways to do specific tests. So you might have some additional questions. Is bonding material 4 significantly different than bonding material 3? There are ways to do tests on that. I'm not going to cover them in this class. If you took a course in design of experiments, you would learn how to do those contrast tests, but I'm not going to do that here. All right. So we conclude there is an interaction, and we'll just use the interaction plot to guide our interpretation for now.